Acín, talk about quantum information.
Okay, thank you very much. Thanks for being here. Yeah, so I was just now told that I will get questions. I hope it is the case. I'm a quantum physicist, and to my knowledge, many of you are not. So I'll try to make actually my course is more about scenarios in which we apply techniques from polynomial optimization, non-commutative polynomial optimization. So why we care about these situations. So maybe it's not so technical. So it's more about concepts and ideas. So let's see how it goes. I also have a question like, who knows that quantum physics deals with Hilbert spaces, vectors, and matrices? Okay, I can assume this is knowledge, okay? But okay, as you will see, I won't have any Hilbert space in my talk, okay? So I mean, if something is unclear, you should interrupt me. So the first part of my talk will focus on what is there, this device. No, yes. On this device-independent scenario, which is basically, I would say, really the place in which we use this. There are many places. Somehow, the main message I want to give you is that quantum physics is a very natural source of problems that have that can be phrased as non-commutative polynomial optimization. I don't know what I'm doing. Let's see. Okay. Okay, this was my first slide, and I will start first by saying, introducing this device-independent scenario that somehow brought us as physicists to the non-commutative polynomial optimization framework. And then I will expand and I will tell you some other applications of this non-commutative polynomial optimization in quantum physics. So I will start by some general slides. So it's a bit of lectures and talk what I prepare for you. I hope it is fine at the end. So basically, I think quantum information science technologies is just a field in which you want to understand what you can do when you put information on quantum particles. So maybe for you it's obvious when I give talks and I use this slide, which is the case here. I spend some time in this first slide because it may seem obvious now, but for instance, I'm a physicist and also a telecommunication engineer. So if you had asked me when I was a student finishing telecommunication engineer, if I thought that putting information on quantum particles would have implied a change on the things you can do with information at that time, I would have said no. Okay, because what I learned at university is that information has nothing to do with physics. I didn't have any course on information in physics. What I knew is that the good thing about information and bits is that I can send you a bit with this being a 0 and this being a 1. This is a bit as good as any other bit. So I think this is why I want to spend some time here. What you have to understand is that the quantum information is a change of paradigm in the way we understand information. So if you put information on quantum particles, you can do some things that you cannot do when you put information on classical particles. This may seem obvious to you. I don't think it is. So the nice thing is that when you deal with information, physics matters. So the laws that describe the devices that you use for information processing matter and fix and give boundaries or possibilities about what you can do with the information you put on these physical devices. Okay, so the field is advancing, and a problem you find is like sometimes now you have commercial devices, okay? You can buy a computer, okay, simulator, maybe not, it's something that you find in labs, but you can buy cryptography, random number generators, okay? And usually these devices are expensive. And when you go to these companies and you buy one of these devices, you say, okay, I want a quantum, I don't know, I want a random number generator, okay? And you get a box, okay? And you take this box and you say, is this quantum? And the company will tell you, yes, it is. And they will charge you a lot of money for that. Okay, so these devices are hard, so there is a problem which is very transversal to the field, which is quantum certification. So you want to know whether these devices behave as expected, and in particular, they achieve something that is impossible in classical information theory because you are paying a lot of money for these applications. And I always use this joke to illustrate what I mean. So this is a joke that is it's based on classical information theory. So this is you are a client, this is your provider, and you want to buy a random number generator, and this is the device you buy. Okay, and of course, you wonder whether this is a proper random number generator. Okay, so this problem, as he says, this is not trivial. Okay, so for instance, what we want to do, we want to achieve a certification of the device from the statistics we see, from the outputs. So we are never going to open the device because we are poor users, we have no knowledge. Maybe we cannot know, but even if we open the device to see if it's a proper quantum random number generator, we wouldn't be able to understand what's going on, okay? We are limited. So we want to certify that this is a proper random number generator, or that this is a quantum computer, or this gives crypto quantum security, or this is a quantum random number generator. This is a problem of certification. And of course, this problem is difficult because the probability that a proper random number generator gives you this sequence is the same as any other sequence, as we all know, okay? Also, to understand why this problem is not easy, sometimes people also mix two notions of randomness. And now I will give you an example, like you have a company and you offer two types of services. The first one, you run Monte Carlo simulations for people. And the other one, you have, okay, it's a bit weird, the company I'm telling you, but okay, you have two services. You can run Monte Carlo simulations and you can offer a virtual casino in the web page. So you need random numbers for the simulations and for the virtual casino. So you go and buy a random number generator. Okay, so what I want to tell you about randomness is that there are two notions of randomness that are fundamentally different. One, the one you use for Monte Carlo, and the other one, what you use for your virtual casino. Okay, so sometimes people say it's the same, but I don't think they are. So I'll give you an example. So you have these companies that offers Monte Carlo simulations and a virtual casino, and you come to me. Let's assume that I'm an experimentalist. And using quantum physics, I can generate randomness, for instance, by sending a photon into a mirror or transmittivity or reflectivity half. So the photon will take this path or this path, and I will detect. So this is like a perfect quantum coin. Okay, so you have random numbers. So I know your business model. So what I do, I generate many random numbers with this setup, but I copy them into a classical memory. And this classical memory is huge, it's very large. I put it into a box, I paint it in fancy colors, and I write quantum random number generator, and I charge you a lot of money for that. Okay, so you come to me, and you buy this box and tell you, okay, this is a quantum random number generator. Okay, you don't trust me, you should never trust me. So what you do, you take this box, and you start generating symbols, and you know people to check randomness, they pass statistical tests. Well, this box, which is just a memory, a USB stick, will pass all tests you can think of. I'm assuming that the tests you will pass are shorter than the memory, okay? Because I have produced these bits with a very good random number generator, okay? So you say, Antonio Acín, nice guy, I will use this for my services. This will work perfectly well for your Monte Carlo simulations, but I take all the money when you use them for your virtual casino. Okay, because these numbers are random to you, but they are not random to me because I have a perfect copy in my setup, okay? So this is, say, statistical randomness, very good for Monte Carlo, but useless for cryptography because I know everything. And this is why also the problem of randomness is hard, because you want things that are not only random to you, but random to everyone, including a possible eavesdropper, which is me in this case. Okay, and again, this is the problem we are facing, okay? So you buy a device, you produce outputs, and you have to infer about properties about the device, classical or quantum, but I will focus on quantum, only from the statistics you see. You are never going to open the device. Okay, if you open the device, you will see maybe there's a memory and not what was supposed to be. But for that, you have to open the device, and we are not going to do that. Okay, so more in general, what we want to do is to certify devices from the outputs. So we have a second motivation for this, which comes from quantum cryptography. Who knows about quantum cryptography here? Eunice? Okay, so the people I know. Okay, so what is quantum cryptography? It's just a method in which there are two, okay, in the cryptography, there are two honest users, Alice and Bob, and they want to exchange a secret message. And what they do, they prepare qubits. Does everyone know about qubits? Okay, just they prepare some states in some quantum particles in some states. Alice prepares these states. Usually, we represent these things as spin particles pointing in a given direction. This is not so important, okay? So they prepare some states, and they send them to the other party, and the other party makes some measurements. So Alice prepares states. She sends the states to Bob. Bob makes measurements. And, okay, they repeat this process. And then Bennett and Brassard, who introduced this protocol in 1984, showed that you can use this process of putting information on quantum particles, Alice putting information on quantum particles, sending these particles to Bob, and Bob making measurements. They proved that you can do a secure information transmission. Okay, you have to believe me for that. I'm not going to explain you quantum cryptography. It's simply, there is a security proof for that. Okay? I can give you more details. I don't think it's the point of my lecture. Okay, so there is a scheme introduced by Bennett and Brassard, in which Alice puts information on quantum particles. She sends these particles to Bob. Bob makes measurements with these qubits. You describe this, everything with these qubits are vectors in a Hilbert space of dimension 2, and the measurements by Bob are matrices in a Hilbert space of dimension 2, and you follow a recipe. And then you can prove that this process gives you a secret that the enemy, that you usually call Eve for eavesdropper, cannot decrypt. And you can prove that because there is a security proof. Okay, so you take these matrices and you can prove that the enemy has no information about the key that Alice and Bob established. I'm not going to do that, okay? I'm just saying that using Hilbert spaces, property of Hilbert spaces, you do the math, and you can prove that the enemy has no clue about a secret key that Alice and Bob established. Okay, nice. It's nice, okay, because you can prove security, okay? And it's also a change of paradigm. So far, cryptography is based on computational security. So cryptographic protocols are secure because the eavesdropper has to solve a problem that is computationally hard. Here, you don't base anything on problems that are hard. You base security on the fact that Alice and Bob encode information on quantum particles. Okay, the security follows from the laws of quantum physics, not from the laws from computational complexity, from the computational complexity of some problems. Okay, it's different. It's a different way of proving security. So the assumption you make is that all what is happening is described by quantum theory, and all the actions by Eve, the enemy, have to be compatible with quantum theory. And as I was telling you, the nice thing is that you can prove security. Okay, so you can use these matrices and vectors, combine them, and prove that Eve has no knowledge about, the enemy has no knowledge about what you are doing. Nice. This is why some people like me like quantum cryptography. Quantum key distribution is actually the more precise name. Now, already more than 15 years ago, there were several teams of researchers, and in particular, Vadim Makarov. At that time, he was in Norway. Not Tromsø, Trondheim, I believe. And what they did, they went to these companies selling quantum cryptography, and they hacked quantum cryptography. And it was a surprise for, at least for people like me, okay? And okay, they made a paper in a nice journal, Nature Photonics, and okay, also Nature and some other journals, of high-impact journals were telling like, wow, first example of quantum hackers. These people went to the companies and hacked the protocols. Now we have to understand how come. So in a way, I was lying to you in what I was telling you. Because, okay. Because I was telling you a few things. So I was telling you that quantum cryptography is based on the validity of quantum physics, and then there is a mathematical security proof. But Makarov hacked quantum cryptography, okay? So what happened? Okay, maybe he found a mistake in the mathematical security proof, okay? Okay, does he look like a mathematician? You see all these cables around? He's not, okay? He's not a mathematician. He's an experimentalist. Okay, so maybe Makarov, he proved quantum physics to be wrong. Well, no, okay, he would have won the Nobel Prize. So my explanation here was too naive, and this was the good thing about quantum hackers, okay? We understood that what we were saying about quantum cryptography was not totally correct. So how come Makarov and coworkers hacked quantum cryptography, despite the existence of security proof based on the validity of quantum physics? Well, and this is the main message we got from Makarov and coworkers. Okay, so we also have to understand that the quantum hackers here are nice and they collaborate with the scientific community. They made the results public. Okay. So what they did, they broke the implementation and not the principle. So what do I mean by this? So there is a very nice theoretical construction. It tells you that Alice has to prepare some states in a Hilbert space of dimension 2, okay, this vector of dimension 2, very simple vector. And Bob has to make some measurements that are described by matrices of dimension 2 times 2, okay, very nice. This is the description of the protocol. And now you have to implement this protocol. So what the companies do is like, look, the way I usually prepare states that go from Alice to Bob is by putting information on light. And to prepare light, I use laser sources. And I have to measure this light. Okay, this is boring experimental physics maybe for you, okay? But what I'm just telling you is that you have to do things with devices. And a device is a laser and a detector, okay? Well, a laser does not live in a Hilbert space of dimension 2, okay? It's a complex object. And a real detector is not described by a matrix of size 2 times 2, okay? It's also a big, well, not big, but it's a real device, okay? So where is the theoretical security proof? Here. And where is the real implementation? There. So the security proof is obtained using some conditions that are never met in practice. So assigning a Hilbert space of dimension 2 is like thinking that your physical device has 2 degrees of freedom. I mean, there is no physical device with 2 degrees of freedom, okay? You take a photon has polarization, frequency. An atom has electronic degrees of freedom, it moves. We all have infinite degrees of freedom. So this initial assumption is never fully satisfied in practice. So for the hackers, in a way, the existence of security proof is irrelevant because it does not apply to the implementation. So Makarov and coworkers could break the implementation without touching the security proof. And this is why they were successful. So what we understand is, for me as a physicist and telecommunication engineer, it's very nice to have an interplay between information and physics. But if your protocols depend a lot on the physical assumptions, on your modeling of the devices, then this might be a problem. Because then you derive conditions about your device under some assumptions that are not satisfied in practice. And this might be a problem. So if we want to make protocols that are robust against these existing hacking attacks, we have to close this gap between what you assume in the theoretical security proof and what you need in the implementation. Because if there is a gap, you will derive a security proof that does not apply to the implementation. Okay, so this is the motivation. And the solution for that is that you have to propose protocols in which this gap disappears, so you don't have to assume anything about your devices. And this is what we call the device-independent approach. So you will model the device with no modeling. So your device will be a black box. And all what you will require is that these uncharacterized devices produce a given statistics. If you are able to prove security or cryptographic solution from a given statistics, all what you need is that the implementation achieves the given statistics. And then there is no gap between theory and implementation, okay? Because all what you need in theory is to observe the given statistics, and all what you have in the implementation is to observe the given statistics. Okay, so this led us to the motivation of this device-independent approach, because you want to make protocols in which you don't model your devices. So if you want, you don't assign any Hilbert space to your device. You don't say, oh, this is a qubit, 100 qubits, millions of qubits, or whatever. You don't say anything about the Hilbert space in your device. It's a Hilbert space because it's a quantum device, but you don't know which one it is. So if you are able to make a protocol for cryptography in this device-independent approach, the gap between theoretical implementations and theory and implementation disappears, and you are robust against the hacking attacks that were existing. So, okay, is it clear what I'm saying? Because I'm going to deal with these formalists all the time. So why is this useful again? Because this also connects to this problem of certification. So Alice and Bob will go to the provider and will say, give me some devices to run cryptography. And the provider will say, okay, here it is. And what do these people get from the provider? Boxes, okay? And this is what I'm telling you, okay? They get boxes. Of course, they have to interact with boxes. How do we interact with boxes? We don't give quantum states, we give classical information, and the boxes give us classical information, okay? We type some instructions on the keyboard, and we see a message from the screen, okay? So we give a message, and we get an output, an input, output. Okay, if you want to see this more, operationally, you get a box. In this box, you have n buttons, and you press button 1, button 2, button 3, button 4, okay? And at the bottom of this box, you have some lights, and when you press one of the buttons, one of the lights is on. But okay, it can be any way, okay? You have a knob that you can put in a given position. You can press a key in your keyboard, okay, and you get a message. All these processors are equally valid, so you give an input and you get an output. So Alice and Bob get these devices from the provider. They spend some time pressing inputs and observing the outputs, pressing buttons and seeing the lights. They can estimate the statistics of Alice observing output A and Bob observing output B when she used input X and Bob used input Y. If out of these statistics they can prove that they can run a cryptographic protocol, then no hacking attack applies to this. Okay, so this is a device-independent scenario. It's a quantum information theory without Hilbert spaces. I will never deal with any Hilbert space. Or it's a quantum information theory with black boxes. Okay? Okay, so this is what I was telling you. Okay, so this is I apply in the context of cryptography. And again, this is also related to this problem of certification. You go to a provider, you get a box, and you want to understand how this box behaves only from the statistics it generates. Okay, how come we can do applications in this minimalistic black box scenario? Okay, why is this possible? So what is the language we are going to use? We are not going to use Hilbert spaces. Okay, so I will connect now my explanation that was based more on operations and providers and money and like practical considerations. I will connect it to perhaps the most fundamental result in quantum physics, which is Bell's theorem. So who knows about Bell's theorem here? Okay, good. I will explain it anyway because it's my favorite result in quantum physics, okay? So in what I was telling you, there is Alice and Bob. They want to run cryptography. They go to the provider and they get some boxes from the provider and they go back. So now the student in my group, Younes, is in Toulouse, okay? So we are here together. We exchange these boxes. I go back to Barcelona and he goes back to Toulouse with our devices. Okay, this is what the reason, the protocol, the scenario I was telling you about, the two people going to the provider, buying the devices and going to several locations. Now we'll do something very simple. I will call the provider a source. So it's a device in the lab that prepares two particles, and these two particles that are entangled, maybe you know this, I assume that you are more or less familiar with this term. These two particles go to two separate places in which you make measurements and you observe the outputs. You see, it's the same, okay? In one case, I talk about users going to the provider. In the other case, I'm talking about experimentalists measuring two particles produced by the source. It's the same. So this device-independent scenario is super connected to Bell's theorem because it's basically the same. I prepare two particles, two systems, two boxes that go to a place, and I make some measurements and I get some outputs. I put an input and I get an output. So, which is a Bell test. Okay, and one of the main lessons of Bell's theorem is that the statistics you see in an experiment in which you do actions on a given device that is causally disconnected from the other device depend on the physical description. And I'm going to elaborate on that. But I want you to remember this, okay? So the probabilities you see in nature somehow depend on the physical theory behind your experiment. Okay, so if you are in classical physics, you will observe some given correlations between these two devices. If you are in quantum physics, you will observe some others. Okay, and if there is potentially a new theory in the future, maybe we will see some other probability distribution between actions on a given place, how these actions are correlated to the actions in the other place. Okay, so now let's become more formal. What I'm talking about? I'm talking about this vector of probabilities that I'm going to call correlations. Okay, so this is, again, this is a vector of probability of Alice seeing A and Bob seeing B when they use input X and Y. And these are just labels, and I will say that there are n possible values. The input can take n possible values, and the output can take r possible values. Okay, this m is because I'm thinking physically that these are n possible measurements given r possible results, but again, it's just labels. Okay, so let's first be mathematicians. Let's characterize this. Okay, so this is the probability of Alice seeing output 1 and Bob seeing output 1 when Alice use output 1 on 1, when Alice use input 1 and Bob use input 1. Okay, this is a probability, a positive number. And then there is a probability that Alice sees output 2 and Bob 1 when they use input 1 and 1. This is a positive number. So on, so on, so on, so on. These are positive numbers. Probabilities are normalized, so they have to sum up to 1. Okay, you have the other combination when Alice uses input 1 and Bob uses input 2. So on, and you have all possible combinations. Okay, I guess everyone follows what I'm saying. It's super simple, okay? It's just probability theory. So this vector of probabilities I'm going to call correlation is just a vector of probabilities, all positive numbers satisfying these normalization conditions. For fixed inputs, the outputs have to be normalized. Okay, I'm not going to deal with Hilbert spaces. I'm going to deal with these vectors in this device-independent scenario because I only care about the statistics. I only care about this vector of measure probabilities. Okay, I will give you an example, okay, for you to touch so that things become tangible. Maybe you don't need it, but okay, let's assume that Alice puts a bit and gets a bit. I can call the bit 0, 1, but I can call it plus and minus. I can call it green and yellow. It doesn't matter, okay? So I'm now going to call it 0 and 1 for the input and plus and minus for the output. I can do that. It doesn't matter. Okay, now let's assume that when Alice measures inputs 0 and Bob input 0, when Alice sees plus, Bob sees plus, and this happens with probability half. Okay? Well, this tells you that this number is half, okay? And let's assume that when Alice sees minus, Bob sees minus, and this happens with probability half. Okay? Okay, who can tell me the value of these two numbers? Very good. Okay, so you see, it's very simple. I'm a simple physicist. Okay, I'm just inventing these numbers for you, okay? We can have fun here, not super funny, but okay, we can do it. I will assume that the same happens when they use input 0 and 1. The same happens when they use input 1 and 0, why not? And now to have a bit of diversity, I will assume that when they use 1 and 1, they get plus minus or minus plus. Okay? Do you see anything wrong with this? No. Okay, good. So I could do this and invent many things. So all what I need is to have positive numbers that are normalized. This, for a mathematician, this is all valid descriptions of a possible experiment. You are not, but I'm a physicist. Okay, so now you will have to understand that this assignment of numbers cannot be arbitrary if you're a physicist. Okay, and this is what I want to tell you, okay? Because physical principles impose limits, give structure to this assignment of numbers. And I think this is a deep message that came from Bell's theorem. Okay, in all what I'm going to do, I'm going to assume that Alice and Bob, or Johannes and I, are in separate locations, and the input-output process is causally disconnected in the two sides. So what Johannes does in Toulouse does not affect what is happening in my device in Barcelona. Okay, I think it's a safe assumption in some cases. I'm going to assume that. Okay, so this is telling me, okay, if you are really paranoid, this is because maybe the events are, you know, space-like separated, that there is no time, not even for light to go from one place to another. Okay, this is telling that what I see in Barcelona does not depend on what he does in Toulouse. So this means that what I see, my marginal probability, does not depend on what the other box does. Okay, so I can write a marginal probability. So if Alice sums over Bob's result, what she sees does not depend on Bob's input. Okay, this is called no signaling. Because if it was the case, Johannes, by choosing an input, he could modify what I see in Barcelona. He will be signaling to me. Okay, I am assuming that this is not happening. Okay, this gives non-trivial conditions on this assignment of numbers. Okay, let's take the example I was naively constructing for you. It was these halves and zeros. Let's see what this party sees, okay, when she presses button 0. And let's see what's the probability that she observes +1 when she measures 0, or she uses input 0. Well, this is the probability of plus and probability of plus minus when she measures 0, Alice, and Bob measures, say, 0. So I'm summing these two numbers, okay? This has to be the same independently of whether this guy used input 0 or 1, because I'm looking at her probabilities. It is, good. Okay, so now this linear constraint is satisfied. Okay, you have to believe me, all the corresponding linear constraints are satisfied because my choice of halves and 0 was not innocent. Okay, so this is an example of no signaling correlations. If you put random positive numbers normalized, you won't satisfy these equalities, of course. Okay, you have to do it carefully to satisfy the equalities. But then this is the set of no signaling correlations, correlations in which what I see in my lab is not causally connected, it cannot signal to me. So here you see a first manifestation of how physics translate into limits on what I call correlation, how the statistics we can see in two different places. So this is not signaling, good. Okay, maybe, how am I supposed to talk for 90 minutes? Is this the way it works? How was Victor? Yes, okay. Eunice, maybe you tell me when I'm like 1:15 or 1 hour 15. Okay, yes, okay. Good, I have it here, yes. Is it 1 hour already that I'm talking? Okay, good. No, yes, good. Sorry, no, yes. Yeah, I started at 11, right? Yes. Good. Okay. So now let's think about how people reason about correlations, about statistics in different places before quantum physics. Yes, okay. Talking too much? Good. Okay, so before, yes, you should interrupt me because when I start talking, I talk and talk. Okay, let's think about let's use common sense to describe how things can be correlated, okay? So the way I reason about this is like, think about the particles coming from the source or you going to the provider and buying these devices. In these devices, there is a program, there is a computer saying, if X is equal to 3, A is equal to 4. Okay, so there is an assignment of outputs to the inputs. And this assignment, the way we reason, is deterministic. Okay, you say, it may be an if clause, but you say if X is equal to 3, then A is equal to 4. If X is equal to 7, A is equal to 2. Okay, you make a table of outputs given the inputs. Okay, so this is what I'm writing here. So the output depends on the input and potentially something that is inside the box that I label by lambda. And maybe this varies in a stochastic way, okay? So if I use my common sense, I would expect that outputs are a deterministic function of the input and something potentially that is inside the box. And maybe this varies stochasticity, okay? You can think of this as in the boxes, there is a small daemon sitting there with some instructions saying, okay, when you see a given input, produce that given output. Okay, so this is written in some instructions. If X is equal to 3, A is equal to 2, or okay, this is written in the instructions of the daemon. Again, these are called in physics Einstein-Podolsky-Rosen correlations, local hidden variable models. To me, beyond terminology, this is common sense. In fact, I don't need quantum physics to describe this. It's the way operationally I would have thought about correlations between different devices before quantum physics. Okay, but I'm a quantum physicist, okay? And if I open a textbook in quantum physics, you will see that it will tell you that, look, probabilities in quantum physics are written in terms of vectors. Okay, can I use, well, I hope I can because all my slides are with the bracket notation. Okay, so if I open a textbook in quantum physics, they will tell you probabilities are just the result of some measurements that are matrices acting on a quantum state. So you need a quantum state for the two systems, a measurement for the first system, tensor product, a measurement for the second system, acting on the state. Okay, these are quantum correlations, quantum probabilities. So some probabilities are quantum. If you can find a Hilbert space, I don't know in which dimension, in which you can define a state and measurements for Alice, measurement for Bob, combine them with the tensor product, compute this overlap, this scalar product, and then this will give you the probabilities. Okay, so some correlations are quantum whenever they can be, there is this Hilbert space in which you can write them in this form. This is the definition according to textbooks in quantum physics. Again, I'm not saying which Hilbert space, okay? Something is compatible with quantum physics, if I can find a Hilbert space, potentially of infinite dimension, in which I define these objects, combine them according to what the textbook tells me, and get the probabilities. Okay, so you see these probabilities, mathematical probabilities I define now, have a structure depending on the physical theory. If they are compatible with no signaling, if they are quantum, or they are classical. Well, it happens that these different sets of probabilities, correlations, are convex objects, and they are strictly included into each other. Okay, so I'm very bad drawing, but I hope you understand what I'm showing here. So the set of classical correlations, meaning those correlations that can be written in this way, is a polytope. It's a convex set, is the one I'm showing here, with a finite number of extreme points. The set of quantum correlations, which is the set that I can write in this form, is also convex, but not a polytope. So it's the red one. And the set of no signaling points is also a polytope. And they are all larger than, so the set of classical correlation is strictly included in the set of quantum correlation, which is strictly included in the set of no signaling correlation. Okay.
Good.
Yes.
In this convex set, is it closed?
Yeah, maybe it's bad, but it's closed. Yes, I mean it's.
Sorry?
What is if it's closed? You said.
It's closed. I mean the set of quantum correlations or whatever you called it.
Yes.
Which is depicted as this red.
The red one. It overlaps here with all the different sets. Okay, so it's this one.
Yes. Is it closed?
Okay, depends on the definition. Take the closure if it's not closed. Yes. Okay, this is a bit technical. Like there are different definitions that let's just take it closed for simplicity. Yes. Okay, so maybe I just stop here for a while, just to recap what I was telling you. So first, I started telling you about devices, you buying devices from a provider, even a random number generator, and you want to certify the outputs, the device from the output, okay? Then I was telling you from hacking attacks, so the problem is that the theory does not meet the implementation, and I was telling you I will work with black boxes, so for sure the theory immediately applies to the implementation, and this led me to now a problem of characterizing sets of correlations. So which, what is the statistics I can expect when observing systems described by different physical theories? Okay, this is what I'm doing at the moment. Now, for you to understand why I have all these different implications, I will explain you Bell's theorem, because it's something super simple, and you will see all these different inclusions, okay? So this is a very quick course on Bell's theorem. And I will do it with the simplest Bell inequality, which is this Clauser-Horn-Shimoni Hall given here. And again, all my talk is about black boxes, okay? So all my lectures. So you have the source that prepares two particles, but again, I model these two particles as black boxes, okay? And you make two measurements, but making two measurements is making a choice, so it's like providing a bit. And then you get a result, it's again a bit. And I will label now this input by 1 and 2, and this output by plus and minus. Okay, so we can make this experiment. We could even play a Bell test here, okay? So I could take you two, bring you to different places, give you a list with bits, and you have to provide a list of bits. We will be playing a Bell test here. We're not going to do it, it's not funny, but we could do it, okay? What I mean by this is that playing a Bell test is like having two devices, two people going to places, asking questions in form of bits, and they have to provide answers in form of bits. And now I take this expression again, y, you'll see why, okay? So you take A1 is the output of this device when you use input 1. And A2 is the output of this device when you use input 1. Okay, I take this expression, CHSH. It will later appear in the exercises, so you should remember it. Okay, let's see what is the maximum of this value in for us, okay? Even using what I say common sense, which is classical physics. Okay, so this output can be plus or minus 1, right? It's written here. So let's compute this maximum of this quantity. I can tell you, this is super simple. It's not one of my exercises, that this value is bounded by 2. Okay, there are many ways of proving that. Perhaps the simplest is that you list all possible assignments of plus and minus ones to the outputs. There are 16, and you will see that you never go beyond plus 2. For instance, you say, okay, the devices will always say plus 1 no matter the input. Okay, this is a possible assignment, okay? So there is a program here that says, forget about X, just output plus 1. Let's compute the value of CHSH. This is plus 1 and this is plus 1. When you multiply, you get a plus 1. Plus 1 times plus 1, it makes 2. Plus 1 times plus 1, it makes 3. Minus plus 1 times plus 1, it makes 2. Okay? Well, we do maths a bit more elaborated than this in my group, but you have to understand that this quantity is 2, and you take all the assignments of plus and minus 1, this quantity is bounded by 2. Is this clear to everyone here that it's bounded by 2? Okay, this is a Bell inequality. So we understand that we expect that in a physical experiment, this quantity will never go beyond 2. Okay, because it's plus and minus 1s. Well, these conditions, I was told, I never checked, but I always tell in these talks, that Boole, the inventor of Boole algebra, had Bell inequalities in some of his papers before quantum physics. Because Bell inequalities are nothing but constraints that you may expect in statistics in between two different places. Okay, this is a Bell inequality. So this is a Bell inequality. This quantity is bounded by 2. Even if this quantity varies with time, because the assignment varies with time, on average, it will never go beyond 2 because the maximum is 2. Is it clear what I'm saying? I guess everyone agrees with that. Yes? I take it to have this sort of frustration so that it's not trivial, okay? So if it was plus, it will be trivially 4, okay? It's still trivial, but a bit less trivial, let's say, okay? Just to have this frustration that for the assignments, I can take some other assignments and there will always be a cancellation. Yes. There is nothing really special here. Okay. So the surprising thing is that now if you take here a state of 2 entangled qubits and you send this here and you make 2 measurements that get 2 outputs, then this quantity goes above 2 and gets 2 square root of 2. So if you are not surprised by the result, my lecture is a failure. I find very surprising that quantum physics goes above 2. Okay, it's a very trivial proof, and quantum physics violates this bound. Okay, so I will say that it's a pity that, I mean, this is done in experiments, in labs. It's a pity that we cannot do it here now, I mean, with our, say, devices, okay? Because, I mean, we cannot do it because of technological reasons, okay? So Younes and I, we cannot prepare a 2-qubit state. I cannot put the qubit in my pocket, okay? So what I'm telling you is that in principle, technologically we cannot do it, but in principle, what we can do, Younes and I, we can prepare this state. He can take one of the qubits, I can take the other qubit. We are sent to 2 different locations. You give me the input. I take the qubit out of my pocket. I make a measurement depending on the input, and I provide an output depending on the measurement result. And you will see that CHSH goes above 2. It's a pity I cannot do it with you now here, okay? But this is done in the labs. I think if we were able even to do it, you could go to the streets. I don't know what is the main street here in Tromsø. In Barcelona is something called La Ramblas. Maybe you know this place, okay? You can go to La Ramblas and you can explain these rules to someone, and I'm sure you will find people willing to bet that this number will never go beyond 2. And then Younes and I, with our qubits and quantum memories, would be beating them and getting a lot of money. This would be the first real application of quantum technologies, okay? We are not there yet, but okay, you have to understand that it's amazing that quantum physics goes beyond 2. I mean, for me, I always find it, it's amazing. Okay, so this is telling you that Using quantum particles, you can observe some statistics that you cannot explain with classical physics, because you can get 2 square root of 2 for CHSH, which is impossible in classical physics. So geometrically, what is happening here? I was telling you that the set of classical correlations is a polytope. A Bell inequality, mathematically, is nothing but a facet of this polytope. It's a hyperplane, and all the set of classical correlations is below this, so this is why you have this CHSH bounded by 2. And quantum physics are above this hyperplane, and this is the violation of the Bell inequality. So quantum correlations achieve this value, which is impossible in classical physics, because all classical physics is here. Actually, you can prove that CHSH is bounded by 2 square root of 2. You will have this as an exercise. So this is, again, a hyperplane, and you know that quantum physics is below that. Okay, you can prove that CHSH cannot go beyond 2 square root of 2. I gave you a realization achieving this. Well, I didn't prove it, but you have to believe me. There is no way you can go beyond 2 square root of 2 in quantum physics. Now, let's prove that you can have probabilities that don't violate these no signaling constraints that go up to 4, okay? Well, it's precisely the table of probabilities I was naively giving you. It's fine now, yes, here, okay? So if you remember my assignment, that was plus, 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 minus, minus, plus, minus, minus, okay? So in this first configuration, A1, B1 is equal to plus, plus, or minus, minus, so the product is plus 1. The product is plus 1. The product is plus 1. And here the product is minus, plus, plus, minus is minus. So you have minus, minus 1, so you get 4 here. Okay, so these innocent probabilities cannot be realized by quantum physics because they give CHSH equal to 4. So you put this assignment here, you get. Is it clear why you get 4? I hope it is. Again, here I was saying that Alice and Bob get plus, plus, or minus, minus. So the product is always plus, plus, plus. And for the last option, they get either plus, minus, or minus, plus. So the product is always minus. So this gives a 4. Okay, so if you make an experiment and you get these very innocent numbers, you are falsifying quantum physics. In the same, this has not happened yet, okay? But just for you to understand that in principle, there are correlations that I can write, I can imagine, I can think of these probabilities. They don't violate anything fundamentally wrong. They are positive, normalized, and I can define my marginal independently of what Younes does. The only problem is that I cannot find any Hilbert space in any possible dimension in which I can define states and measurements giving me these numbers. Okay, so I don't know where to, sometimes when I give this talk in front of experimentalists, they come to me and say, where can I find these probabilities? Well, I don't know. I reason in terms of quantum physics Hilbert spaces, okay? But one day, maybe someone will find points here and you will be falsifying quantum physics. Okay, so now, again, it's long. I talk too much. I was telling you with devices, and now I'm discussing about correlations in nature according to the theories. I'm a quantum physicist, so I care about this region. Okay, this is nice. Sometimes I have papers working here, but I don't know any theory giving me probabilities here, so I don't work so much on these things. I mostly work on what I can do with quantum physics. Well, I have to understand how quantum black boxes behave, so I have to understand this region here. Yes?
Inequalities for the entries of this matrix?
No, this is a probability distribution. Assignment, I came to this, sorry. This is an assignment of probabilities to this experiment. Okay, so I was having, this is the same as CHSH, is defined for an experiment in which you put an input bit and you get an output bit. Okay? I can invent numbers for these probabilities. Okay, you see, I was assigning numbers to this. So this is what you will see in the experiment. Out of these probabilities, you can compute, out of this experiment, you can compute functionals. These are functional, okay? So this output will be sometimes +1 when the input is 1, and this is what I call A1, okay? So this is a functional of the experiment, okay? It's the output of the first box when I use input 1, okay? And so it's like we have these boxes, and we have two buttons, we call 1 and 2. And we have two lights, and we call plus and -1. So A1 is when you press button 1, you tell me whether the output was plus or -1. This is A1. It's a variable, a random variable, if you want. It's which light is on when you press button 1. If it's the light to the left, you call it +1. If the light to the right, you call it -1. Okay? And of course, this varies with time. You can compute the expectation value, and this. Okay, so this is operationally, you will spend some time pressing the buttons and looking at the lights. So if you press button 1 and I press button 1, we will be computing this number here. Okay, this is your output when you press button 1 times my output when I press button 1. Okay? Now, this number will depend on the probabilities behind my experiment. So usually when you make an experiment, you think of some probabilities giving you the input-output relations, and you count frequencies, and from these frequencies, you reconstruct the probabilities. If you flip a coin, it has a probability of having heads Q. You flip it many times, and out of the sequences, you estimate Q. I'm doing something similar, but I'm only estimating this number here. I count, okay, out of the things, you measure 1 and I measure 1, or you press button 1 and 1, how many times I got plus and how many times I got minus, and this gives me the expectation value of this quantity.
The constraint you have on the matrix is that the sum of each row is 1.
Yes. Well, I want to compute this. Okay, you have to understand, maybe. Where's the chalk? Okay, maybe I'll write it mathematically. I don't have it here. I want to compute the expectation value of this quantity, which is I don't know if you can read what I'm writing here, okay? So I want to compute the expectation value of this quantity. This quantity is equal to +1 when you and I see plus and plus, and we both use input 1. And it's also plus when we saw minus, minus, okay? Plus -1 times the probability of minus plus plus minus. This is this number here. It's a function of the probabilities behind my experiment.
This being at most 2 is a quality of the entries.
Yes. So I write it in this term because it's the way it's written, but you can reinterpret it as a linear combination of the table of probabilities that I had. Yes. This is why, say, this here, the screen represents this. All what I'm dealing with is a vector, in this case, of 16 numbers. This depends on the size of the input and the output. You will have a vector of many numbers, okay? Not all of them are linearly, they are positive. Not all of them are linearly independent because they sum up to 1, okay? They also satisfy the non-signaling constraints. These are other equalities, okay? So you can interpret now the screen as the space where these correlations live. And this is a linear combination of those. It's a hyperplane. And the slope is fixed, and I move it, changing the independent term. If you want to have it, okay? So at 2, this is the classical set, and I shift it, and I'm in the quantum set. It's a hyperplane, yes. A linear combination of the probabilities. Yes?
You say that there is a source
acting on the boxes.
Mhm.
So what does it mean? You have which does it go into some
The source?
Yeah, specific model.
But no, exactly. It can be any model. So it can be the two users going to the provider and buying two devices, or it can be an experimentalist preparing two particles and making measurements on that. Or it can be you going to a shop in which you buy two instruments and you play two, and you get two notes. I mean, it can be any model. There is no model. This is device independent. There is no model for that. Any experiment, it can be you and I going to a place in which you get these two boxes and we press buttons and we see lights, or we put a knob in two different positions. And it can be any situation in which you have two devices potentially prepared by someone else. This is why they are correlated, in which we put an input and we get an output. There is no model. This is why it's device independent. I'm just reasoning about statistics I can see. I mean, you and I going to a provider, getting boxes, or an experimentalist preparing two particles and making measurement in two different places. I mean, I don't know. Think of any situation in which you have two systems in which you put a bit and you get a bit.
And what's the arrow? What's the meaning of your?
The arrow is like you put an input and you get an output. Well, if you want, this somehow represents the causal connections. So these particles had a common past because they were created by the provider or by the source. So there was here a common cause for our stuff, okay? They came, and now you do an action on your device and you get an output. And your action is potentially correlated to my action because they had the same origin. If you get two devices that they never talk to each other, we will never see correlations, okay? Because I will see something independent of what you have, okay? For me to see something that are correlated to what you have, they have to come from a common origin. This is what I'm representing by the source. If we never talk, what I see is independent of what you have, unless there was a common origin in the past. This is what I'm representing.
Then it could be for the case where you get 4 instead of 2 squared.
Well, in quantum physics, it's impossible to get a 4. You can prove it.
Why?
Well, because I cannot find a Hilbert space. I cannot find vectors and measurements in matrices in Hilbert spaces that I combine and I get 4. So I mean, there is a papers in our physics community where people say, why I don't get 4? I mean, and then the physics will tell you, because I cannot find Hilbert spaces in which I find these objects and I combine them and I get 4. So for a physicist, this is not a super satisfactory answer, reasoning in terms of Hilbert spaces. So people are trying to get if maybe there is a deeper reason why I don't get 4. I can tell you more about this, okay? But at the moment, the main reason is because we physicists, quantum physicists, we reason in terms of Hilbert spaces, and I cannot give you a 4 in terms of Hilbert spaces. As a quantum information theorist, I want to make protocols using Hilbert spaces, so I have to understand about this region here.
So the correlation matrices are some special construction.
Remember that the screen represents the correlation matrices. They have to live there, yes.
Hilbert space.
Yes, which I don't know because I don't want to assign any Hilbert space to my device, which is a quantum black box. It has a Hilbert space, but I don't know which one it is.
Passing X in as some.
No, X is just a label, it's a beta, measurement 1. And the box chooses the operator for you. You don't pass any operator. So you say the box is fully uncharacterized, it's a quantum black box. So you say, okay, bit is 1. And the box takes this bit, does a quantum action on whatever is inside the box, and that was coming from the provider, and gives you back a bit. Mm-hmm. Mm-hmm.
Where does that enter?
Again, A1, B1 is a function of probabilities, okay? In quantum physics, these probabilities have this form. So I take this form, I put it here. I have a function of the state and the measurements here. I put it there, and I will never get a 4. Okay? And the reason why the problem is not trivial is because I have this tensor product. So there is a measurement for one box and a measurement for the other box. Okay?
So this notation A1, B1, and so on. This devices always give back classical bits, right?
Yes.
But whatever bit you take for A1, B1, and so on, you never can exceed
2.
2.
Well, you can, yes.
Why? I don't understand how you get to 2 square root.
Yes, I'm surprised you don't understand, but it happens. Yes, it has been proven. Okay, maybe I anticipate a bit. The mathematical demonstration is super simple, no? We didn't make any mistake in multiplying plus and minus ones, okay? So I will tell you what we accept with that, okay? There are 2 possibilities, okay? This proof has been derived under 2 conditions. The first one is that this output-input process was not causally connected to this input-output process. So if you want, in this, Alice's output does not depend on Y. Okay, this is a constraint, okay? So you can think of a computer program inside the box 1 that says, if X is equal to 3, A is equal to 4. It doesn't say, if X is equal to 3 and Y is equal to 7, A is equal to that, okay? This is why I don't put a Y there. This is an assumption, okay? And it's an important assumption. And the second one is that I thought that these values were defined before choosing the input. Okay? They have well-defined values. Once you buy these things, this has to be 2. I agree with you. So this means that the assumptions were wrong.
No, I mean, I understand why under this assumption that we are requesting so classical devices, we have this bound 2.
Yes.
What I don't understand is how you can see.
You mean operationally, or I mean what I'm telling you is, well, okay. Well, you do the following, okay? So maybe I didn't put it as an exercise, but what you do, maybe this is a good exercise. You take the state I was giving you. You take the operators I was given in my, I was not given them, but okay, I can give them to you. You put them here, you compute quantumly, you take this term, you replace in CHSH, and you get the square root of 2. I cannot say more than this. I mean, nature behaves according to Hilbert spaces. I can define these operators and states in Hilbert spaces. I put them together, and it gives me 2 square root of 2. I go to the lab, and I see 2 square root of 2. This is why I'm telling you it's a pity that I cannot do it here, because you would see it with your eyes that it's happening. Or we could go and get the money from people in the streets, yes. Well, I'm happy, yes.
It's a not understand model. So you always get just +1 or -1.
Yes. Okay, there is something important here. And this is something you cannot do in quantum physics. You cannot ask the 2 bits at the same time in quantum physics. You cannot make, okay, this is maybe a bit quantum. In quantum physics, you cannot measure 2 non-commutative observables at the same time. So either you ask 1 or 2, but not, so you cannot make an experiment which you say, tell me the output for A1 and for A2 at the same time. Not sure if this helps, but this is a difference. Look, this is not intuitive, okay? So I don't pretend you to say, oh, sure, it can be 2 square root of 2, because it's not. What I'm saying is that I can define this task, this problem operationally. Again, I will go, yes. Oh, you want to, yes. Yeah, that's comment.
Of expectation value is, because here at the moment he is only considering plus ones and minus ones, and then it's super puzzling to get a square root of 2. To add on top that you are like the expectation values of
Yes.
vector.
Yes. Okay. So yes, and each round it will be a plus or minus one, but these things.
If I put in some random unitary matrix.
Yes. Yes.
And you take bracelet here.
Yes.
But I cannot bring this together with what you told, that the output is just plus one or minus one.
No, the output will vary, okay, from round to round. Sometimes it will be plus one and sometimes it will be minus one. But if you take the expectation value and you compute this thing, you will get 2 square root of 2. So actually what happens in the quantum experiment is that and you take the operators I was giving you, you will see, if you made the calculation, they are all equal to 1 square root of 2. I don't know, maybe we can talk later. I mean, you don't, it's normal you don't understand because it's not intuitive, okay? But I can make for you, I cannot, but it's people do experiments in which they prepare 2 systems. These 2 systems go to 2 different places. You make 2 measurements, but 2 measurements, you can simply see that you choose to implement measurement 1, which is bit 1 or bit equal to 1, bit equal to 2. This is, you can model this as a black box, and depending on the bit 1 or 2, you implement a given measurement or not, and you get an output that you call plus and minus 1, and you accumulate statistics, you estimate frequencies, you plug them here, and you get these numbers, and you get 4 times 1 over square root of 2, which is 2 square root of 2. I'm sorry, but nature behaves this way. I'm not saying that it's intuitive, but it's the way nature behaves. Yes, this has been proven. Huh?
And then this is some sort of form on the tensor versus CH.
This is the mathematical formula I'm using, yes.
CH formula.
Yes.
What is the definition of that function?
Well, okay. So this CHSH is just a function of the observed probabilities. Okay? No, this is a general definition. Look, I'm dealing with objects in this black box picture. I only care about inputs, outputs. Let me just finish, okay? And then you. So this is the definition. Now, what happens is that the form of these probabilities, I mean, nature is about probabilities. And we do theories to explain probabilities. When we do theories, we explain probabilities through mathematical objects. But this is statistics, okay? And now you will tell me, in my theories, in theory, I explain these probabilities according to a mathematical formalism, okay? And now in quantum physics, we explain these probabilities according to Hilbert spaces. Okay, now, sorry, I interrupted you.
And let's say that you have many more X's and Y's and A's.
Yes. No problem, okay? So I will have more operators acting on a given state. Oh, well, then I will have to adapt this. Okay, what you have to understand is that maybe it's a good point. So the Bell inequalities are these hyperplanes, okay? These hyperplanes defines the space of probabilities that have a classical description. And this object only depends on the number of inputs and outputs. If you give me the number of inputs and outputs, I can construct this convex set, and there are programs that, given a convex set, gives me the facets. Okay? In the past, people found CHSH a la physics way, Okay, I believe that I should put a -1 here, as you were asking me, like why the -1? Intuitive, in an intuitive way, okay? Today, you come to me, you say, well, maybe not to me, because it's a long time I don't run programs, okay? But let's say to someone in my group, and you say, okay, I'm making a measurement, a situation in which I have 2 measurements of 2 outputs. You give this, you make a program, and the program gives you the Bell inequalities. And it will give you this. And now you tell me, no, I have 3 measurements of 4 outputs. You make a program, you know how the convex set looks like, and the program gives you the facets. And these are all the relevant Bell inequalities. So maybe I explain more with the hands, but now we have a very good understanding of this object, and we can run convex optimization techniques, and you will have all the facets, which are the Bell inequalities. I'm not sure if I'm answering your question, but this is routine now.
Right for but it's an expectation.
Yes.
So it's not the value, it's not the product of the values, it's an expectation of.
Yes, sorry, yes. I mean, at each round, you choose a given input. So you are computing one of the 4 elements there. Okay, because sometimes we choose input 1 and 1, so we are measuring this. Sometimes 1 and 2, we're measuring this, okay? So you have to accumulate all these rounds, and we even leave the possibility that these values change according to some probability. But I can, of course, also compute it for deterministic assignments, okay?
There are sometimes putting -1.
They can do whatever they want.
Yeah.
But I don't need to trust what is happening in the box. The only thing I want to trust is the value of CHSH, because I observe it with my eyes. How the box achieves this value, I don't know, and I don't care. I spend time pressing buttons, collecting lights, and I can compute CHSH without caring about how my box works. I simply see that my box produces 2 square root of 2. You had a question or no?
I think it would be much clearer if because there's a strategy, right?
Quantum strategy, yes.
With these relations we have talked so far, they depend on a strategy between the 2 parts.
Yes.
And the only difference between the classical and the quantum is that there's a certain strategy that is a different stage.
Well, this is what I was telling you. This is theory independent. I can define without defining any theory, because it's just a linear combination of probabilities. Now, the theory tells me how these probabilities look like. In the classical case, I have these deterministic assignments. In the quantum case, I have this expectation, I don't know, scalar products of operators, let's say, okay?
And then it also becomes very simple.
I mean, if you write some given probabilities here, you will have some simplifications, yes. But this is the definition without here. And now you come and you invent a quaternionic ultra-relativistic theory. I can still define this, okay? Now you will simply change how these probabilities are computed within your theory. So this is why I'm telling you that the theory tells you what you see in the experiment and the value of this quantity. But this quantity you can define without any reference to any theory. It's just you get this input, output, and you observe the statistics. Okay. I was very ambitious in the things I wanted to tell you, but I'm for sure not going to get there. But I think it's nice because I'm happy to get questions. So I will finish this part with, again, we care about this region here because I'm a quantum physicist and we want to make protocols in this black box picture. So in the case of CHSH, we know, and you will prove it, that this value is bounded by 2 square root of 2. Now, this is where the first time we encountered non-commutative polynomial optimization was when we tried to characterize this red quantum region of Bell inequality violation, okay? This is interesting because it's the region in which we can potentially achieve things that are not possible in classical information theory, because these are points that have no classical analog, potentially interesting to do things that are not possible in classical information theory. Okay, so what is the problem? So now imagine you were an experimentalist and you were doing this experiment where you prepare two particles and you make two measurements of two outputs, precisely the same as in CHSH. Now I call the choice of the input 0 and 1. Before it was 1 and 2. It doesn't matter, okay? It's just a label. And you observe these probabilities. It's not the half, 0, 0, half, 0, 0, half that I wrote before. It's just some numbers that I invented for you. They are normalized, they satisfy or whatever. Okay, is this quantum or not? Okay, maybe we have experiments in which we are falsifying quantum physics and we didn't know, okay? So what I'm asking you is if this point is here or outside. Okay, who knows the answer to that? It's a very simple problem, okay? You see, 16 numbers. Okay, so this problem is hard, okay? Why it's hard? Because I want to know whether it's quantum, so I will try to reproduce this number with some operators. First, I will try with dimension 2. I will fail. Does it mean that they are not quantum? No, I should try dimension 3. I will fail. Dimension 4, I will fail. So you have to run over all possible Hilbert spaces to exclude all possible quantum explanations. This is why the problem is hard. Actually, this problem is Turing undecidable. Deciding whether a point has a quantum realization is Turing undecidable. I didn't prove that, but it has been proven. So it's really hard. Okay, so I will tell you about this later.
Mathematician, so psi is a vector and has a product of two Hilbert spaces.
Yes.
And the two ends are operators of those.
Yes, yes.
That's a problem.
Yes. Well, okay. What I demand, very good. So I should be more formal, okay? What I'm asking is, you give me these numbers. Now, tell me if you can find a Hilbert space for Alice, a Hilbert space for Bob. Now the tensor product of the two. Define a vector in these composite Hilbert spaces, and define sets of operators, of projectors for the Alice's Hilbert space and Bob's Hilbert space. Put everything together with tensor products and combine with the ket and give me the probabilities I was given. Is it clear now? Maybe. Okay. And I want you to know whether there exists a Hilbert space. Okay. I'm not saying it has to be qubits, dimension 4, 300. Okay. It can be any dimension. This is why the problem is Turing undecidable, because I'm not fixing the Hilbert space dimension. If I fix the Hilbert space dimension, the problem would be decidable, okay? Because I could run all the possibilities.
Actually, you're asking, does this right? Do the coordinates of P have some algebraic right?
I would say so, but
This orange boundary, this is something where there is no polynomial that vanishes.
no, yes.
There is no separator, which is polynomial. They tell you yes, no.
But this doesn't sound like
Well,
this doesn't sound like inequality. You're asking, is this matrix parameterized by something?
Yeah, okay, but I mean, this will fix, I'm not fixing the dimension, okay? So it can be, the number of parameters is not fixed in my parameterization. So I'm not sure if this is, you see, I mean, I believe the problem you're referring to is decidable because you're fixing the number of parameters, right? While what I'm telling you, I'm not fixing. Okay, this can be, I don't know in which Hilbert space these objects live or act on.
X, MBY, and psi extended to this expression.
No, okay, if you fix the dimension, for instance, then the number of parameters is fixed by the dimension, yes.
I see, so it's not, so MA, X, and BY can be any size, psi can be X.
The only thing I demand is that they are projectors in that Hilbert space, uncharacterized Hilbert space and arbitrary, and they sum to the identity in this uncharacterized Hilbert space. You had the question, yes?
Yes. Is it possible?
What?
Is it possible to come?
Okay, wait, you will come, yes. But okay, there are two ways, okay? Before what I'm going to tell you now, okay? People were doing, okay, this is like, you can think of the experimentalists getting these numbers and going to the theories, and the theories will be saying, okay, I'm going to see if I can do it with Hilbert space of dimension 2. and he was writing matrices, then the problem becomes what you are telling me. You parameterize your matrices, and now you want to see whether you can get these numbers. And the theories fail. So he goes back to the experimentalist and says, I couldn't, maybe your experiment is wrong. And then the experimentalist says, no, I'm pretty sure it's correct. Maybe your model is wrong. And then the theory says, okay, I'm going to try now with matrices of size 3 times 3, okay? And goes and fails and goes back, okay? And then, like this can be forever. This is why it's Turing undecidable, because they, okay. Okay, so this is, in this context, we introduce what is called now the Navasquez-Pironia hierarchy, NPA. I'm not sure if Victor referred to that, but it's basically, it will become non-commutative polynomial optimization. But it was introduced in this context. So basically, what we gave is a hierarchy of tests, and we proved that this is convergent, that approximate the set of quantum correlations from outside. So if you want a pictorial way, these are sets that define semi-definite, are instances of semi-definite programming, okay? And they approximate the set of quantum correlations from the outside. So basically what we do now is that if you give me some numbers, I will check, okay, in principle, all those are included, so I could check the largest, but sometimes we start by the first, which is the simplest. So I will check whether the correlations you gave me are in one of these sets. If they are, they may be quantum. But if they are not, for sure they are not quantum. Okay? Because they are outer approximations. And the NPA hierarchy gives you the way of constructing these outer approximations, and it tells you the recipe you have to follow. In all these SDPs that you have, the size of the matrices grows. This is called the level of the hierarchy. The size of the matrices involved in the SDP grow with the level. Asymptotically, you go to infinite size matrices, but you can prove that you converge to the set of quantum correlations. I'm not going to, yes, maybe. Yes, okay, very good, yes. This is in my exercise, but actually what we have to do, and this is good that Victor mentioned, is that I don't solve this problem, but instead of asking about tensor product, I demand that the operators commute. So if operators are tensor product, so instead of writing this, I remove the tensor product here, but I demand that Alice's measurements compute with both measurements. I think if you ask physicists, people are undecided about what is the right formalist, okay? So if you talk to people doing quantum field theory, they will go for the commuting formalist. More quantum info people will go to the tensor product. So this is a good point that unfortunately I didn't put in my slide. We remove that and we add here a tensor commutation between the measurements. Yeah, sorry. This is a problem that I didn't, sorry. Maybe for you, it would have been simpler to define this way. I was explaining everything with this formalist. I'm more used to this, okay? But for some people, measurements in a given region in space-time and measurements in another region in space-time define commuting operators. So they will write you things. And this is just postulates of the theory, okay? So yes, but we don't know what is the... Okay, so this is a possible definition of quantum correlation. This is another possible definition. These are just definitions, what is what I'm saying, okay? And we know this. So the NPA works with this. Since this contains this, okay, it depends on how you want to see it, okay? So NPA levels are still outer approximations to the quantum set, but they converge to this set. Not to this one, which is strictly smaller than the one here. Now, if you ask physicists which one is the proper one, I don't think we have an answer to that. It depends on, yes, how you. Again, I will repeat what I just said, okay? Reality is made of probabilities. How you explain probabilities depends on your theory. I can make a theory in which I combine objects according to this rule or according to this rule. These are just theories.
How should I think of this phi?
This is the state.
Cyclic vector, or
this is a normalized vector. Okay, sorry. So in quantum physics, the first postulate tells you to any system comes with a Hilbert space. Okay, this is what it has. And the state of my system is given by a complex Hilbert space. And the state of my system is a normalized vector in this space. This is the psi. So is this my particles is a system, physical system. So it has a Hilbert space attached to it, which is the tensor product of the Hilbert space of the two particles, according to the postulates. And the state of my two particles will be a normalized vector in this Hilbert space. And this is what I'm representing here.
Besides just.
It's a vector in a Hilbert space. Yes, because quantum physics works with Hilbert spaces. Yes?
So in the commuting model, is it known whether we actually need to know infinite dimensional?
Okay, so in the commuting, okay, these two sets are the same if they are finite dimensional. And the gap appears when you go to infinite dimensional Hilbert spaces.
But in the second line or in the first line?
Well, a gap means that I can give you objects in the infinite dimensional Hilbert spaces here that you cannot write in this form.
I see.
Okay, probabilities that have this that I cannot write in this form. It's a good question. I would say both, but I don't know. I would need to check. Yes, I mean, here you are pushing me a bit out of my comfort zone. So I would need to, yes, I would need to check. Yeah. Okay, so this point is not quantum. The point I was telling you, okay? It fails at given level of the hierarchy. I don't remember which one, okay? So you see the theories, instead of going back and forth and making calculations, can run one of the levels of the hierarchy and go to experimentally and say, you should better check your numbers because either you have an amazing result or there is something wrong in your experiment. And I think it's maybe a good moment to stop because I'm already talking too much. Okay.